So as our X-linked recessive example, we're going to use red-green color blindness because it's a trait that's common and that we observe in humans. You'll notice that in our family tree, the same one that I've been using in the other examples, I colored in two squares, person 2-3 and person 3-1. And that's why I need those Roman and Arabic numbers so that I can identify people in the family tree without having to know their names. Now, when a trait is X-linked recessive, the points over on the side, those are your clues. The first clue I always look for is whether males are affected more than females. Typically with X-linked recessive traits, males are almost exclusively affected. That doesn't mean females can't be affected. It just means that it's more likely that males are affected. If you think back to X-linked recessive traits, males only had to have one copy to have the trait, whereas females had to have two copies, which is why it's less likely that females will have an X-linked recessive trait. The second point is a really important one, especially when you're considering sex-linked traits. There is no father-to-son transmission, none. Fathers do not pass X chromosomes on to their sons, they pass on Y chromosomes. But all daughters of affected fathers will at the very least be a carrier. They might even be affected if their mom passes the trait on to them as well. So for number 2, you could add the words at least carriers. They might even be affected. Now, depending on the condition, sometimes a carrier female, so a female who has one X chromosome with the recessive trait and one without it, sometimes they might have some mild manifestation of whatever disorder it is. It's not true in all cases, but sometimes they might. So that's a piece of evidence that could be present in the context of a question. Now 4 and 5 are all about the chances, and so those are a little bit tougher to use as pieces of evidence because they're just chances or predictions. But if a female is a carrier, she has a 50% chance of having an affected son. Her son is going to get one of her X chromosomes, and if he inherits the one that has the recessive trait, then he's going to have that trait. She also has a 50% chance of having a carrier daughter for the same logic. Now the last point is a point of interest here, really. The first affected son in a family might have inherited the gene from a carrier mother, or it might be the result of a mutation, and that's something you have to keep in mind. Sometimes the first time a trait shows up, it's because it's actually been hiding in that family's genetic code for a long time, but no one had the right combination until then. Other times, though, it's because a mutation happened in that particular individual to cause that particular trait. Now, if we take a look at my family tree and we consider grandma and grandpa, their 3 kids, their kids' spouses, and all of their grandkids, anybody who has the trait that I'm studying, I colored in. So since this was about red-green color blindness, I colored in the symbols for the people who have that condition. That means that everybody whose symbol is white still doesn't have color blindness, has normal color vision. Since color blindness is recessive, for everybody who has normal vision, I gave them one X chromosome with a capital letter. I was using R's here for red-green color blindness, but really the letter you chose is not the most important thing. You'll notice that anytime I had a male whose symbol wasn't colored in, his genotype was determined. Males have one X and one Y chromosome. So, for example, person 3-2 wasn't colorblind, so they got the dominant allele on their X chromosome, and their other sex chromosome is a Y, genotype certain. So for all of the males who were not colorblind, so person 1-1, 2-2, 2-5, 3-2, and 3-5, I knew their genotype right away. For all of the males who were affected, I also knew their genotype right away, because of course on their one X chromosome they had to have the recessive allele. For all of the females, none of them were colorblind. So every female in my pedigree has at least one copy, like grandma, of an X chromosome with the dominant allele for normal vision. However, some of them were carriers. I knew that person 1-2 was a carrier because she had a son who was colorblind. Her son could not have inherited his X chromosome from dad. He has to have inherited it from mom, so she must be a carrier. The same is true for person 2-1. She had a son who was colorblind. He could not have inherited that from his father, so he must have inherited it from his mother. For more or less the same reason, person 3-4 was heterozygous as well. This time, I knew that she was heterozygous because her father was colorblind. And so the thing up here says, daughters of affected fathers will be carriers. She has to get an X chromosome from her father, and that's the only X chromosome he has to pass on to her. The rest of the females, you'll see I put question marks. So person 2-4, 2-6, 3-3, and 3-6. I don't have enough information. They might be a carrier or they might not. I would need to see more data to be certain. You'll find that it's really hard to prove that someone is homozygous dominant for a trait. It's easier to prove that they're heterozygous because you just need one example of offspring that has the recessive allele. But in those scenarios, I don't have enough data. They might be carriers, but they also might not be. So if I was to ask you about those people on a test, their genotype would be uncertain, and I would have to give two possibilities. Either they're homozygous dominant or they're heterozygous. Either way, they're not colorblind. Now that's X-linked recessive. Does anyone want to ask any questions about that one? Okay. Next pattern of inheritance that you might see, X-linked dominant. So it's the same family, same pedigree the whole time. That's why I gave you those handouts of all those copies of the same family. A couple of examples of, or an example of a trait that's X-linked dominant is something called hypophosphatemia, which is otherwise known as Rickets. Now, some of the clues that you would look for the X-linked dominant pattern of inheritance. First, affected males transmit the traits to all of their daughters and none of their sons. That's pretty forceful wording, all and none. We were always certain that fathers don't pass X-linked traits on to their sons. In the last example, though, we said that their daughters would be carriers, at least. But now we're saying affected males transmit the trait to all of their daughters. Affected females, because they have two X chromosomes, will at the very least transmit the trait to half their sons and half their daughters. That is assuming that my affected female is heterozygous. If my affected female happens to be homozygous for the trait, then that probability would increase. Now, the third one has some wishy-washy wording compared to the other two. There are usually twice as many affected females as affected males. So that's usually, which means that sometimes it won't be that way. For this one, I put the number of males and females as kind of the last piece of evidence, whereas for X-linked recessive, it was right at the top because it's a really good piece of evidence. It's a little tougher to tell sometimes with a dominant trait because usually there are so many people who have it that sometimes you don't see this distinctive ratio between males and females. So if you look at my example, I did color in 4 females and only 2 males. So my ratio was twice as many females. But they often express the condition to a milder degree. So that might be indicated in the context, but not always. So if you look at my family, I colored in person 1-2. She has the trait. In the second generation, person 1 and 3 have it. And in the third generation, 2, 3, and 4 all have the trait as well. So everybody who has the trait got an X chromosome with a capital letter D for my vitamin D resistant rickets. Anybody who did not have the trait got 1 or 2 X chromosomes with the recessive allele. It depended whether they were male or female. all of the unaffected males have the same genotype as grandpa, person 1-1. X chromosome with the recessive allele and a Y chromosome. So it'd be the same for person 2-6 and the same for person 3-6. Or sorry, not 2-6, 2-5 and 3-5. Now for all the females who were unaffected, they got 2 X chromosomes with the recessive allele. So person 2-2, 2-4, 2-6, and 3-6 all got 2 of those. Since the trait was X-linked dominant, if you don't have it, you must not have a copy of the dominant allele. Now for those who were affected, if they were male, their genotype was certain right away. Their X chromosome had that dominant allele, and then they had a Y chromosome. For my females, so grandma and her daughter, and where are we looking down here? My last 2 people at the bottom. If I look at their genotypes, I kind of underlined the second one with blue, and I said for affected females, either the parents or the children helped me determine that their second allele was the recessive one. So for example, in the case of grandma, she has 3 children. One of them is a son over here who doesn't have the condition. He had to get his X chromosome from her, so I know she had the recessive allele. If I look at these 2 children at the very bottom here, they both had a parent in each case who had to have passed the recessive allele on to them, and so that's how I know that they were heterozygous. Now you don't always have to fill in everybody's genotype in a pedigree. I'm asking you to do so on your assignment so that you can practice. But it would be realistic for a test question to pick a couple of people and ask you what's their genotype, or if they had another child, what are the potential outcomes, which is why I'm showing you how we figured out everybody's genotype. Now there's just one more and then we'll have a break. Does anyone want to ask anything about either X-linked recessive or X-linked dominant patterns of inheritance? Yeah. For just a second, sure. Did you have a question or you just need to see something? Okay, then our last one is Y-linked. Same family. Y-linked traits, you'll remember, only affect males. There's a gene called the SOX gene that could result in hair loss that's Y-linked. The piece of evidence that you need to look for is that only males are affected. And only is important. When it was X-linked recessive, there were mostly males or almost always males. And so sometimes people mix up X-linked recessive and Y-linked. So you got to look at the second clue. If it were Y-linked, every affected male, that's a strong word, every affected male has an affected father, affected sons, and affected brothers. Every single male in a line would be affected. If you don't see that, then it's not Y-linked. Then it would have to be X-linked recessive. So if I take a look at this family up here, Grandpa was affected. On his Y chromosome, I wrote the letter S for the SOX gene, but I wrote nothing on the X chromosome because it's not on the X chromosome, it's only on the Y chromosome. So when it was X-linked, I wrote the letters on the X chromosome. If it's Y-linked, I write them on the Y chromosome. All of the females just get 2 X chromosomes because they cannot possibly have this trait, not unless something else happens. But in our simplified version here, they're not getting it because their X chromosomes aren't Y chromosomes. And if I look, every male in a line is affected. So person 2-3 and 2-5 are the sons of person 1-1. So they have to be affected because they got their Y chromosomes from him. Person 2-3 has a son, so his son is affected. Now you might ask yourself over here, why is person 2-2 unaffected? Well, person 2-2 isn't from the same line. I don't know who his parents are. I have no information on them. He is the husband of that person, or the person she's having kids with, and he does not have the same parental line as her, and so he is not affected. Since he is unaffected, their sons are unaffected. Even though in person 2-1's family, all of the males are affected, she doesn't have that Y chromosome, so she can't pass it on. So no females have Y chromosomes, so they're all unaffected. Any affected male has the allele on his Y chromosome as long as he's part of that line. Now that brings us